Testing 1 2 test. Testing. Oh wow. Testing 1 2. Testing 1 2. Test 1 2. Test 1 2. Testing 1 2. Test 1 2. Test 1 2. Testing 1 2.
Okay, everyone, welcome. We're going to get started now. So I'd like to welcome friends and family to the Nanoscience Lab A 2023 final presentations at the California Nanosystems Institute, or the CNSI at UCLA. My name is Dr. Shailene Tanimoto, and I am the education manager here at the CNSI. And I've been with your students for the past week, watching them learn and grow. And we are very excited to show you all that they've learned. And so first, I'd like to welcome you to UCLA. UCLA was founded in 1919, and it is the second oldest UC or school in the UC system. Our campus spans 419 acres. We have 337 undergrad and graduate degree programs, about 31,600 undergrads, and about 13,500 of those students are in the life and physical sciences. And so we're here today at the CNSI at UCLA. We are one of Governor Gray Davis's Institutes for Science Innovation. The CNSI here at UCLA was established in 2001 as an engine for innovation. And our mission is to be a world-leading nexus of research, education, and translational activities by engaging in scientific discovery that fuels innovation and impacts society. And so CNSI, we are a department here at UCLA, but we're not a degree-granting department. You cannot, unfortunately, major in nanoscience yet. But instead, we are an interdisciplinary hub of research, technology, education, and entrepreneurship. And so our education outreach programs include K-12 teacher training workshops in nanoscience experiments, a nanovation competition for 6th through 12th graders that happens during the academic year. We also do a lot of public outreach demonstrations throughout the Los Angeles area. And then a big thing that we do in the summer are these summer session programs for high school students. And so this Nanoscience Lab course is a 1-week program for students to learn nanoscience concepts through hands-on nanoscience experiments. And they were also able to tour some of our technology centers and use instruments to analyze the samples that they prepared in their experiments in the morning. And so we just want to give a special thanks to some of the people that helped throughout this week teach your students. And so first, I'd like to thank all of our instructors. So these are all graduate students and undergrads here at UCLA from a variety of different backgrounds. So from the Department of Chemistry and Biochemistry, Physics and Astronomy, Bioengineering, Mechanical Engineering, and we had a lot of them come throughout the week, taking time out of their busy research schedules to come and teach students on subjects in their expertise. So thank you, instructors. Your students also had some guest lectures throughout the week, and these lecturers talked about their journey from high school to where they are now, how they got interested in the scientific fields that they study, and some different career paths that students can have through science. And so we'd like to thank Professor Rodriguez from the Department of Chemistry and Biochemistry. That's me. I was a guest lecturer, even though I'm not a guest. And Dr. Mark Van Zee, who's a postdoc in the DiCarlo lab. So thank you. We'd also like to thank our resident assistants, Ethan, Kylie, and Ashley. They have been living in the dorms with your students for the past week. So let's just take a moment to acknowledge that. So thank you for all the patience and kindness that you have exhibited over the past week with these students. Okay, and then like I said, your students got to tour a lot of our technology centers here, and a lot of our CNSI event staff have helped a lot to put on this event, including our live stream that's happening right now. So we'd like to thank our technology staff from the Advanced Light Microscopy and Spectroscopy Lab, the EICN, which is electron microscopes, the Nano Pico Characterization Lab, and the Clean Room. And then our CNSI staff that helped to get us food throughout the week, and then help us with audio, visual, IT, and our digital communications, so putting on this YouTube live stream. Thank you to our CNSI staff as well. Okay, so the goal of our Nanoscience Lab class is to give students an exposure to advanced topics in nanoscience and the development of life skills and science communication. And so each night after their experiments that they performed, they were given a homework assignment. And this homework assignment was to draw a picture that explains the essence of the experiment that they learned without making a literal figure explaining the science. And so this should be something that's understandable to someone who's unfamiliar with nanoscience or the topic that these students learn about. So this is a very, very challenging homework assignment, but it's a very important form of scientific communication. So this was something they had to really understand the concepts so that they could create an analogy that made sense and captured the essence of these concepts. So it's very challenging, and they're going to present some pictures that other students drew, and they're going to walk you through what the picture shows, the nanoscience concepts that are present, and the limitations of the analogy. Sarah, would you like to say something before we begin?
Okay, so I just wanted to add my welcome to all of the parents. It has been a pleasure getting to spend some time talking with your students this week. Let me just briefly introduce myself. My name is Sarah Tolbert, and I'm a professor in the Department of Chemistry and Biochemistry, and also in the Department of Material Science and Engineering, and I'm the faculty director of this program. And I'm the one who actually assigns the grades, but don't worry, it's a pass, no pass class, so it's not like I'm really making choices on grades. So I just wanted to take a second to thank the parents for lending us your children for a week. Thank all of the participants. There was a lot of enthusiasm and a lot of really good questions about science talks. And then also just give the parents a little more orientation about the presentations that we're about to see. Okay, so communicating science is one of the biggest challenges facing our society right now, in that there's a lot of misunderstanding of science, a lot of mistrust of science, and part of that is based on an inability to communicate the essence of a scientific result without overhyping it and without underselling it. And that balance is a real challenge. And it is a well-known fact that humans are visual creatures, and that if you can create a visual representation of a concept, that people will remember that concept for a significantly longer period of time. And so one of the things that happens, so I do some cool research in my lab and I publish a high-profile paper, and some newspaper article says, I want to write an article about it. And the first thing they ask is, what is an analogy to an everyday concept that I can use to explain this concept to the general public? And those analogies are really hard to come up with. If you want to do it right, so that you are truly capturing the scientific essence of the result in a correct manner. So it's something that we grapple with as scientists all the time. Every paper that we publish, we make a graphical abstract where we try to create a simple cartoon version of the major results. And so we tasked your students every night with coming up with such a cartoon analogy of the key results of the science. One of my own teenagers did this program last year, and I can tell you that even somebody who's had nanoscience dumped on their head since they were 2 years old did not find it trivial to come up with a good analogy that captures the essence of these experiments. But nonetheless, everybody persevered and everybody did it and came up with cool things. And then what we have done is we have picked a few of what we consider to be the coolest graphical analogies, and they are going to be presented today, but not by the person who drew them. So they are going to be presented by a different group. And they do not know who drew them, and they have not been allowed to consult with who drew them. So they must just use their own scientific knowledge of what they did to explain what is going on. And they're going to talk to you about what is the science, how it is captured in this cartoon, what the cartoon is showing, and also, really importantly, what are the limitations of the cartoon. And I just want to say to all the students, please be careful of your language in that every cartoon has limitations. If it's not the real system, it cannot capture every aspect of the system. That's expected. And those are the limitations of the analogy, but they are not what the cartoonist did wrong or what the cartoon is missing or the errors in the cartoon. Because it is the nature of an analogy that it cannot capture everything. So please try to remember that when you're describing it. Everybody's worked hard here. We don't want to diss anybody. And these are what we consider to be the best analogies that captured the largest amount of the science. Okay, so they're going to present this, and then we're going to open the floor to questions. And I also want to just talk briefly about questions. I can tell you that when my graduate students go off to give talks at high-powered conferences, they're not afraid of giving talks. They've stood up in front of people a million times. They know they can talk about their science. The thing that always scares everybody is, what if they ask me a question I don't know the answer to? That's what always scares everybody. Eventually you realize even if they ask you a question you don't know the answer to, you can come up with something relevant enough. It may not exactly answer the question. That's a great way to deal with questions you don't know the answer to. You sort of answer something related you do know the answer to. I'm giving you guys a hint on what to do if you're stuck. But the point is, what you realize is it's not that scary to be up here and answering questions. But the only way to realize that is to just do it. To get a question you didn't know the answer to, and to realize that the world didn't end. And so the questions are a super important part, and that is where you, parents, come in, because you have to ask them questions. Other people in the program, you are also welcome to ask them questions, but you parents must answer questions. And just to inspire you, I will tell you that if you, parents, do not answer questions, ask questions, I will ask a lot of questions. And my questions are generally harder than your questions. So you may save your children by coming up with a whole bunch of questions. Okay, so with that, let us get started. And hopefully this will be a fun and learning experience. And hopefully that you, the audience, will learn about a bunch of nano concepts that your students learned about over the course of this week.
Okay, so this is our schedule for today. And as you can tell, we're already behind. But it'll be okay. We've cooked some time in, so it'll be all right. Yeah, we'll cut the intermission. It'll be fine. Okay, so I just want to give a few tips for the students. They have not had time to practice up here. But we have 3 microphones, so 1 for everybody in the group. We also have some laser pointing devices so that you can point to things in the in your picture to help guide the eye. And then super important, can I get this mic? Do I have to turn it up? So just push this button there. Okay, perfect. So really important about these microphones is that you want to pretend to be a pop star. Okay, so when your head moves, the microphone moves with you. You want to hold it like a pop star and not like an ice cream cone, or else people can't hear you in the microphone. Nobody in the live stream can hear me right now. So you have to hold it like a pop star and not an ice cream cone. Pop star, ice cream cone. Okay? So okay. All right. Really close to it too, okay? So even when I bring the microphone around to the audience, hold it close so that we can hear you. Really important for people on the live stream. Okay, so group 1, are we ready? Come on up.
good. Hey y'all. I hope y'all are doing really well today. I'm Navia,
I'm Ashley.
And I'm Jacob.
and we're gonna be explaining this analogy for you guys and about like measurements at the nanoscale. So I'm gonna be running through exactly what we see literally here in the analogy. So let's start with the first slide. So we see a rabbit coming into the store, this restaurant for example, and then we see this frog who's thinking, does she want a square? Does she want a rabbit? And then we see a little light bulb, which means like, oh my god, I think I know what she wants. Because on the menu you see exactly what the options are, and she already went through them. And then on the second slide, we have the frog at the cashier asking, how many do you want? The rabbit says, I would like 2. And at the bottom it shows how, I'm assuming 1 cookie means $4, and then 2 would mean $8. On the bottom left slide, we have the rabbit is presented with 2 cookies, one with sprinkles and one without sprinkles. And then the rabbit shows like concern the rabbit is like, I would like the one without sprinkles, because they're like a little happy sign, and the one with sprinkles makes me like mad. And then at the very end, they're all kind of happy, but then she presents the frog with a coupon, or $8, so then her overall total is $0.
Okay. And then I'm going to be explaining, I guess, the science concepts behind each image and what they kind of mean. So in the first image, when she's just walking in, or the bunny is walking in, this is a really great example of indirect measurement, which is basically where you take a measurement that you know, or measurement that can easily be found, and then use that to find an unknown measurement. So through her asking about the square and the triangle, she can figure out what the rabbit wants. She can figure out that the rabbit wants the circle. And then in the second image, it's talking about constructive interference, which is basically where when 2 wavelengths interact, or like overlap, they kind of combine and then create a larger wavelength with a higher amplitude. So then here, 1 cookie, or circle, I guess, is $4, but then when she asks for 2 of them and they kind of combine, it creates $8. And then in this bottom picture here, it's depicting how things at the nanoscale I guess influence things at the human scale. So basically, nanoparticles have different properties than bulk particles, or like bulk objects. For example, they have a higher surface area, so they're more reactive. And then in this image, the sprinkles are kind of representing the nanoparticles because they're very small. And it's showing how small things can kind of have like a big effect, because if the bunny gets the one without sprinkles, she's happy, but if she gets the one with sprinkles, then she's upset. And then the last image is showing deconstructive interference, which is basically where when the 2 wavelengths interact, they kind of cancel each other out. And this is shown through the coupon and then the price. And the coupon cancel out the price of the cookies, and then it creates 0. So, yeah.
All right, so I'm going to be talking about the limitations of this image right here. And so basically, for a bit of background, we have 5 questions that we have to base our analogy off of. Now, you don't have to answer every question because it's almost impossible. But so there's questions, and you have to try to make the analogy. So one of the questions that this image didn't particularly capture is the use of the AFM, which is a atomic force microscope, and that uses a specific point, such as like an atom, a really, really small point, to try and map out a certain object. Now this isn't exactly recognized in this image, but yeah, it's important. And the main use of the AFM is that with a light microscope, you can get pretty high resolution, but you can't get the most exact resolution that you can possibly get, which is by using the AFM, because it uses a point, and the point is exactly used to map out the object. The smaller the point, the more resolution you can map it out with. And so, for example, if your point is an electron, super small, you can map it out exactly what it looks like, which is pretty impressive. And then another question that they didn't answer is how you can use light as a measurement. Now, you can use light as a measurement for small things and for big things. For example, small things microscope, pretty easy one. They use light to measure out and examine what small things look like cells that we can't see with our own eyes. And for large things, this isn't really as known as much, but LiDAR, which probably most of you haven't heard of, it's when you use like objects in the sky that emit light and lasers, and you can map out like from space, the world basically looks like geography and urban planning, and that can be used where you can't see the objects close enough from way in outer space. So when you're far out and you use the light, you can map out a lot more closely and use light to map out things much bigger that just aren't possible with just naked eye and from far away. And another thing that she did mention, but I felt like wasn't exactly precise, which is okay, is the indirect measurement. So what Ashley said, indirect measurement is when you get something that is already measured, like a small thing, that can be used to measure another thing that it can't directly be measured and exact. So in the first slide, you can see the square question mark, triangle question mark. Oh, it has to be the circle. And so that's not a bad example of indirect measurement, but normally what this means is that for measurements, let's say you have an object that's 2 electrons long, but you know the object next to it is 4 times the size, but obviously you can't measure it, so it's just 8 electrons long. But that's one of the small limitations, but it's not bad. And this is what that image limits, but besides that, it's a really great image.
Okay, questions from our audience, please. Or else I'm handing it to Professor Tolbert. I'll start with you and then...
Okay, so I think you guys did a great job of explaining this. But I think that, so there's one thing I wanted you to talk about in terms of a limitation. So in terms of constructive and destructive interference. So you guys got the concept of adding and canceling. But what kind of systems do constructive and destructive interference generally apply to? Generally not concrete things like money.
Yeah, so for constructive and destructive interference, it normally applies to wavelengths. When the wavelengths combine and like light and, for example, metal, when they oscillate, they combine and they make peaks. And then when they do constructive interference, the troughs come together and they cancel each other out. So normally it's not concrete things like this, but with the analogy at least, it shows the peak, which is their price. The peak represents the price. When they come together, they make the peak, and then the coupon represents the troughs in essence. Or when they come together, they make a trough, they cancel each other out, and then they make 0.
Yeah, no, but that's exactly the right thing. It generally applies to waves, and the idea is that waves all have pluses and minuses, and it's the phase. It's how those waves are interacting or overlapped with each other. And I think that that's definitely something, it's just not capturable in this cartoon.
Yeah, I would say a really good example of this would be ripples in a pond when you drop 2 stones and you see the waves going out, and then if you have 2 stones very close, you can see their ripples kind of collide, and you can see areas where the waves are much higher and areas where the waves are much lower, which is constructive and destructive interference very literally. Any other questions?
Dr. Rita Blake's questions are also challenging.
So one thing that you mentioned that I wanted to, pun intended, probe a little bit more into is the AFM. So you mentioned that one of the advantages is resolution, which for sure is an advantage. Can you remember, I don't even know if it's an advantage, but just another distinction as to what an AFM can get you that a light microscope cannot?
Well, one of the main things is just the size, obviously. But another thing is, for example, I don't know really how to word this, but the AFM uses touch, right? So it touches things and it scans over them. And what that can do is also kind of give you insight of the inside of what it looks like, because it takes high resolution touches and images and just can probe more in the inside and feel the like the squishiness or the resistance of the texture, which kind of can give you an idea of how hard it is or soft it is, and that can be used in medical purposes as well to see what in one of the labs that we saw is a rat aorta, and they used the AFM to go and probe it, and through the touching instead of using the light, they get sense parts oh that's a hard part, that's a soft part. We could use that and put antibiotics through that, and now it hold up. But maybe that if you put antibiotics through it, it wouldn't hold up because it might just collapse because it's too soft.
Any last questions from the audience? Okay, let's thank this group and move on to group 2. Group 2. Oh, yeah. Who is our artist? Princess. Okay, is there anything else you'd like to comment about this that maybe they missed or misinterpreted?
Not
Just closer. Just
okay.
pop star.
Not really. I feel like the group really covered what I was trying to go for, and yeah.
Well, great job. It's very cute. Group 2.
Why do seagulls fly over the sea? 'Cause if they flew over a bay, there'd be bagels. I'm Lex.
I'm Rachel.
Oh wait, it's on now. Okay. I'm Logan. And we'll be introducing plasmon resonance in nanoparticles.
Okay, so first I'll be describing what's happening in this image. So here, this is like a depiction of some kind of video game setting, and it's split into 3 different parts. And in the first part, our character is being hit by 2 triangle-shaped particles, and in the second part, these triangles turn black and shoot out of the character. And in the second part, there are 3 triangles shooting at our character, and you can see that in the second part that they all just kind of go through it without hitting the character. And in the third part, there's also 3 triangles going towards the character, except this time the black triangle converts into some sort of lightning ball energy for the character, while the white ones kind of just bounce off of the character.
Alright, so I will be introducing the key concepts because plasmon resonance is kind of confusing. So the first key concept would be plasmon resonance. So plasmon resonance is essentially when a sea of electrons, delocalized or free electrons in a metallic substance, when they interact with an electromagnetic radiation or light that matches with the wavelength that causes them to move, they will absorb that light and transmit the complementary light or the opposite light. And so that's plasmon resonance. An example of that, and like an analogy, would be a swing, basically. So if you have a swing and you're like pushing someone, if you push at the right time, it will make their swing higher. But if you like push at random times, it'll kind of just like, they will like just like move around. They won't really swing. A second key concept is what does the observed color due to plasmon resonance depend on? So there's 2 main things that it depends on, and that that would be our shape and our size of the particle. So the shape of the particle would basically change how plasmon resonance affects particle. Basically, the shape will cause the light to be reflected or like hit the shape differently, which will change how you observe the particle, and the size would change it because it would reflect differently. So it would basically just change how you see it. A difference between transmission and light scattering. So light transmission would be when the light passes through an object. So a good example of that would be like water or ice. So you have light and it passes through and you can see it. Light scattering would be when the water, or would be snow. So like the water, sorry, it would be snow and the light would bounce off the snow. So it's like going through the object versus like bouncing off of it. And our last key concept is the photothermal effect. So the photothermal effect is essentially when you have a particle, and if you put light on it, the particle will absorb the light, and that light will be turned into energy and will cause the particle to move. So, yeah.
Yeah, so this image shows a lot of these things. Over here, there are 3 triangles going into the character. I assume it's a character. It looks like a video game. And there's a lightning bolt here that shows that the photothermal effect because it's heating up. There's also these are also scattering off of the character because these white triangles were pointing this way, heading this way, and now they've gone off in different directions. They've showed that the size and shape of the particle has an effect on what you observe from it, the light that comes off of it. In the first one, there's these 2 over here, and it goes out this way, and there's 3 over here, and these 2 are black over here, and when these 2 go in, these 3, they're the same color, and over here they change color, and this shows transmission as it goes through the character, and I think that's about it.
Okay, there are some limitations to like this image's analogy. Like for example, plasma resonance is defined by oscillating electrons which match up with the wavelength of a light, which will in turn display an opposite color. And I believe that the top section is trying to depict that, and it did not really show a sort of resonance, more of just the reflection of an opposite color. But this is understandable in this kind of setting, I would say. And yeah, I think this picture depicts the concepts pretty well.
All right, questions from the audience.
Thank you, Shailene. Also, wonderful job explaining the concepts in this illustration. So I kind of want to start with one of the first things that you described, which was you correctly stated that what is important for this phenomenon to occur is that you have this free sea of electrons in a metallic particle. I guess my question is, why is it important for this to be a nanoscale particle? What about that leads to plasmon resonance?
Do you want me to answer that?
Any of you.
Okay, so from my understanding is if you just have something that's metallic, it will reflect light differently, but if you have a nanoparticle, because it's smaller than the wavelength of observable light, it will have a different effect on how you perceive that light.
So I guess my question is, do we see plasmon resonance in larger metals? And why might you not?
No, I honestly, I'm not sure, but I guess honestly, I'm not sure, but yeah, I don't know. So it's not. Yeah, so basically the size and shape of the particle is like what's most important. But when you have like a bulk material, it's just observed differently. I don't know how else to word it.
Okay, I think it's okay to not know the answers. So well done, like navigating answering the question. I guess think about the fact that when you have a nanoparticle, the number of total electrons or the atoms in that is a lot smaller. So what might that do for them being able to resonate?
All right, I guess I'll try to answer. So basically, basically when there's less electrons, I guess they can more freely flow through the particle. I'm not actually sure about that.
You're really close. So essentially the idea is that because you have a small particle, you have the ability for all the electrons to be moving together. So all to one end, and then when they reverse with the wavelength, when they're resonating, they'll all move to the other end. Whereas if you have something like a bulk metal, the electrons are not going to all be moving to one side or the other. It's just too large of a system. So it's kind of this ability for them to be moving in sync with each other in that way. But nice job.
Our grad student instructor questions are also challenging.
So I just want to start by saying this is the hardest physics of any of the experiments. So luck of the draw. Okay, so I have a question about the top one, where you talked about the fact that one color goes in and then the complementary color comes out. In a real experiment, to see that you absorb one color and reflect another, what colors have to be incident upon the sample? If you, like, for example, if you just shown red light on a sample, can green light come out?
I'm not sure I really understand your question. Could you reword it or repeat it?
Or do you have do you also need me to? So you talked about about the way colors look, and the fact that you absorb one color and you see a complementary color. And you commented that white things come into the particle and black things come out. But I think that there is a limit in this cartoon that is not quite capturing the physics in terms of, is it possible to shine, for example, red light on your nanoparticles and have blue or green light come out?
Then that would be not true.
In your experiment, what did you actually do?
It was more of like the nanoparticles within that formed the color. Like we didn't really.
What light did you shine on them?
White
light. So you shone white light on it, and then just pretend that the whole rainbow, we're just going to call it, there's like a red half and a blue-green half. We're going to forget the subtleties. So you shone white light on it. What color did they look when you looked at your samples?
Like I shone red light on it?
No, you shone white light on it. And then what color did they look?
It looked red.
They looked ruby red. So what color light was not, what color light bounced off the samples and made it to your eye?
Well, red.
Red. And what color light was shown on the sample and did not make it to your eye?
Green.
Green. So how could they change? How could you change this cartoon to capture that? I would change the very first panel. Pretend for a moment that little white triangles are green light and little black triangles are red light. What could you add?
Or you could add light from both of them. So if red was representing white, you could add in some green ones, which is black.
Exactly. You could have both white and black triangles coming in and then only black triangles going out. And that would more describe the actual physics of this system.
Okay, I think that was good. Okay, so who is our artist? Anything that you'd like to add about this or that they did not fully describe?
So I feel like they really captured it. There wasn't really anything much else, I feel like. So yeah, good job.
Okay, thank you. Group 3.
So, hello. Oh, okay. I'm Eric.
I'm Mackenzie.
And I'm Oscar.
And today we're going to talk about an analogy for emotion, and I'm going to talk about what we literally see. So on the first image, the first scenario, there's a Yankee stadium, which they're playing basketball, and there's Yankee fans cheering inside the stadium, and outside the entrance, there's Red Sox fans dissing about Yankees. And then for the second scenario, there's Red Sox stadium, and which the Red Sox fans cheering for their team, and Yankees fans hating the Red Sox. And then at the last diagram, we got a championship, which both Red Sox and Yankee fans sit together and watch the game.
All right, so we see many scientific concepts here, but the first one that I want to highlight is hydrophobic versus hydrophilic, which is basically just water-fearing versus water-loving. And so we see hydrophobic demonstrated because the Red Sox fans are not associating and they're not mixing with the Yankee fans at both of these scenarios, which are like normal conditions. And then we also see hydrophilic because there's one fan here, which I don't know if you can read it, but it says "Boo Red Sox," which doesn't necessarily mean that he's a Yankees fan, but he's still mixing with all the other Yankees fans, which shows how they still can mix because they share certain properties. And then we also see an emulsion going on here at the championship game, which is a fine dispersion of minute droplets of one liquid into another, which usually which are not soluble. And so we see obviously the Yankees fans and the Red Sox fans who are mixing together under the championship game, which is like the emulsion. And then it's because the championship game interacts with both teams. They're both inclined to go and cheer for their team. And then we do see amphiphilic here, which is the being able to mix with both polar and non-polar things, basically water and things that are hydrophobic. And so this character right here, I'm going to have to read it off here. Basically, he's rooting for the rivalry rather than each individual team. So he's able to interact with both at the same time. And yeah.
So now I'm going to be describing the limitations or like concepts they couldn't quite capture in this image. So first is mechanical energy and how it affects emulsion. So essentially, the idea behind the concept is that more mechanical energy means like the particles can break down more and it's able to mix for a longer amount of time. So, for example, in the water and oil like lab we did, we all know that water and oil don't mix. So when you pour one into another, it just separates into two separate liquids. But in the lab, we saw how mechanical energy from the frother that we were mixing it with allowed the particles from each substance to become smaller and allowing the two insoluble liquids to mix and break down, which formed a more stable and longer lasting emulsion. And another limitation is that we didn't see something representing a microfluidic device, which is a device that combines two liquids at a smaller level. So by breaking down particles, so they're able to flow more laminarly than turbulently. And an idea we had to add to this analogy so they could represent that is showing a scene where two like groups of fans are entering the stadium, one in a stampede and one versus like a single file line. So the stampede can represent the turbulent flow, because when multiple or a group of people are trying to enter through a small gate at one time, it'll be very like chaotic and it'll be take longer for all of them to enter versus if they were to enter in a single file line, it would show laminar flow, and which basically means flows more smoothly. And if it was a single file line, everyone would just be able to go through the gate. So also, we just thought that there was a little bit too much dialogue and words in this analogy. So kind of like the issue with that is just people might not be able to quite understand the image without a lot of the dialogue. For example, like the fans that are like the fans from other stadiums that are in the stadium, so Red Sox fans in the Yankee stadium, like if they were just standing there without dialogue, we wouldn't really be able to understand that the idea behind like the analogy that they're trying to represent. But overall, we thought that this image was like really great and it captured a lot of the concepts really well.
Questions from the audience, please.
Okay. First off, I want to say, I could totally see you're trying to like explain to some random person, like what is this hydrophobic interaction? It's like one molecule is a Yankees fan and one molecule is a Red Sox fan. You could totally get this across to people. So awesome on that. So there's a couple of concepts that I would like you to talk about and how they are or aren't represented and how they possibly could be represented. And one of those two concepts are the role of surfactants and microphase separation as opposed to atomic mixing. If you could talk about either of those two. Well, so did your emulsion contain only oil and water?
No. So with like in different tubes, we had oil, water, and then a emulsifier or a stabilizing agent, which like
Okay,
when
so that's what I meant by surfactant. Sorry. Could you talk about the role of emulsifiers?
Yeah. So basically, the emulsifier is, at least a good emulsifier is something that has properties of both. Like we used soy lecithin, and it had a nonpolar tail and then a polar phosphate group, I'm pretty sure. And so that was able to interact with both the water and the oil, and it made for a more stable emulsion.
Okay, so is there an emulsifier in here?
Well, the emulsifier, at least from what we saw, was the championship game, and how that's what really brought the two fans together, because they wanted to go cheer for the team, but they had to interact, and it kind of, the championship game is able to interact with both of the fans. They're both drawn to it, and just like an emulsifier.
Okay, that's a great explanation. In a reality, an emulsifier is usually just another molecule. So probably it should be a person or a thing, because it is not, it's not an overarching concept to the emulsion. It's just another component. And then my other question is, in an emulsion, are the oil and the water totally mixed up?
No, so basically, in an emulsion, it's usually fine droplets of one in another. So basically, oil and water would be fine droplets of water and oil, or oil and water.
So it's not necessarily that they're like mixing together. It's almost that it's like a temporary fix to mixing it together, because since the two liquids are insoluble, it means that normally they're unable to mix. So when we add an emulsifier, or we add, like how I talked about, certain amounts of mechanical energy, then it just allows for the particles to be broken down even more, and smaller particles just means that, like, essentially it's just going to take longer for it to go back to its original form. So in, like, for example, our lab, we saw that when we stirred it, the particles were so big because there was just like not a lot of mechanical energy or an emulsifier or other components that were able to break down the particles a lot. So we were left with like bigger particles of oil in the water. But when we were using the frother, it allowed the particles to break down really smallly, and so it just appeared that it had been completely mixed together. But after some time, it will obviously like separate. But it was just kind of like I would say a temporary fix.
I want to go back to Shailene, but is that captured anyway in this picture, or how could you make it captured?
Well, it's kind of captured in the sense that after the game, they go back to, not mixing with one another, and so it's kind of a temporary fix of sort of they're in the same stadium together versus at their usual times they're usually just separated.
Well, that's something that we could assume, but I think maybe if they added that, it would be more clear. But that's just kind of something that you have to assume, like, what a championship game, is like kind of like a one-time thing. So you would just assume that the fans like kind of separate again after, but I think it wasn't really super clear in the image.
Any other questions from the audience? Okay. Okay, thank you. Oh, who is our artist? Jacob, anything that you'd like to add?
I thought they did a pretty good job at kind of encapsulating mostly what I meant to say. The Yankee Red Sox championship, like the century-long thing. So I thought it'd be cool to add that. But yeah.
Awesome. Great job. Okay, group 4, come on up.
Hello, my name is Angela Pak.
My name is Angel Yu.
My name is Tejas.
And this is our picture, and there is a big forest with many trees, and people is killing the tree and building the river. And the river first separating for like 4 different parts, and like keep separating it for like 2 parts as the boat goes. Also the waterways become smaller and smaller, and person become happy and safe when he goes to like a smaller place, and people on fire in the like bigger waterways. And lastly, people feel not happy to be in the water that is not become smaller anymore.
Okay, so I'll be explaining the analogy in our picture. So our topic for this was photolithography. So basically so if you guys recognize photo from maybe like photosynthesis or even just photo, that just means light. And photolithography is a process in which you print on like a pattern or like any texture onto something using light. So basically photolithography has 6 steps. So the first step is coating, and then in photolithography, how does this work? They coat the whatever like thing they're printing on with the photoresist. So in this first step number 1, you can see that the constructors are choosing where they want to like build the river, and that's the same with like coding and just picking where we want our pattern to be. And then in step number 2, in photolithography, this is masking. So then basically they're picking out, or like they're choosing exactly where they want to work. So then you can see right here that they're like coning off this area. And then in step number 3 of photolithography is to expose, and that basically means that you're gonna like set it out for like the sun or just UV. So in our case, the constructors are burning the trees, so like deforestation isn't really good, guys. But yeah, so they're burning the trees, and then in step 4 is develop. So then in the development stage, you're going to either remove the part that was exposed to UV, which is positive, or the part that wasn't touched by the UV, so like underneath a pattern, and that would be negative. So in our case, it's positive, because the part that was touched by UV in our analogy, which is the fire, is all gone. And then step number 5 is etching. So that's basically like you're carving out the part in like the metal or just like in the thing that you want. So in our analogy, they're cutting out the soil to make room for the riverbank. And then step 6, in photolithography, this step is known as stripping, and it's basically just cleaning up your component. So then in our case, the water, sorry, my hand is like really shaky, but the water is clearing out like all the excess dirt and stuff that we don't need anymore from that was still left over from step 5. And then we had a lot of other concepts in this lab, because it also, because like photolithography is usually used to make computer components. So like another computer component that was in here that we talked about was transistors. So these are made of a semiconductor material, and then they're commonly used in like computer logics, like ones and zeros. These are how like computers can like compute numbers, like can process information. So then down here you can see a 1 and a 0. These are the binary numbers, and these like basically your computer is just a whole bunch of 1s and 0s like working and processing. So then we can see a transistor, like the 1 path here and a 0 path here, to show the computer processing. And then if you can see like right here, it says, okay, it's not really clear to like anyone back there, but it says in 2 years this will double. So this connects to Moore's law, which is a law that was observed by Moore, who basically said that in every 2 years, the number of transistors in an area will increase by 2. So then in our case, you can see this 1 path increasing, but it's not like fully increased. So this shows like it'll be eventually increased. And then also down here, if you can see, like there's like a lot of paths. So then this is, and then you can see like this one guy like right here working on a path. So he's saying, I'm more precise with my shovel, with my tiny shovel actually. So this represents a concept that we learned that was called feature size. So basically, in photolithography, like we use UV, right? But then you can increase the precision of like whatever pattern you're doing by using shorter wavelengths. So then we can see that compared to like a big like construction zone, like this guy like down here is like single-handedly like doing like a whole new river, and then like it's a lot skinnier than like this big river up here. So then that shows here. And then also feature size, the smaller the components, as you were taught, there's going to be an increased need for cooling. So then, because like there's a lot more things in like one area, so it's a lot more denser. So then here you can see that while they're on a river, like it's like the temperature here is like really high, and then if you can see like right here, like it's on fire. So like that isn't good, obviously, like especially like 'cause they're near a river. So yeah, they don't want to like be set on fire. And then it says here that these like rivers are really efficient, right? 'Cause they're small, because like more dense means that there's more components, which means that there's a greater efficiency and that you can fit in one location.
So now moving towards the limitations. So looking at the first one, we see how the first one that she mentioned was coding. So one way we could have, the author could have made this a little bit better, was to explain a little bit more how the coding works. It's kind of little bit unclear, but another way they could have done this is by explaining what the coding method was, but it just shows the trees. And another thing that they did was they used a little bit too much words here explaining, because without the words here you wouldn't really know what's going on. But overall they did a really good job implementing all these concepts together, which not many of us could do. So big props. And something else, this was a super long unit, so some things that we didn't that they didn't incorporate was resistance versus resistivity. So basic resistance is the measure of opposing the flow of currents. So basically, that is measured by ohm, the symbol, and conductors or semiconductors are basically the materials that that has low resistivity, and the longer the material, the more the resistance, and the bigger the area, or the surface area, is the less the resistance. Another thing that they forgot to mention was the clean room. So basically, they asked us what was the purpose of the clean room, and why we couldn't incorporate, why it needs to be clean in a sanitary environment. So basically, the reason for that is because when using semiconductors in an industrial sense, we do not want to incorporate environmental applications inside that environment, because it would obviously damage the semiconductor. And another thing that that they didn't implement was that use of SEMs. So basically, that is it's basically scanning electron microscope, which uses electrons rather than light waves, that allows you to look at more specific areas in the material compared to light waves, because electrons are obviously smaller than light waves, allowing us to look deeper into the material. So essentially, electrons would reflect off the material, creating a image on what is presented in a material.
Thank you.
So this is a lot. There's a lot of stuff to talk about here, and I think you guys really did hit on a lot of them. I think there might be one extra thing here that relates to one of the topics. So in the middle, there's a little gate called the Hydra gate. Can you think of what that might relate to in the lab that you were learning about?
Hi? Hello? Okay, so I think the Hydra gate might be representing like this is also like connected to transistors, in my opinion. So like transistors, they're either a 1 or a 0, right? And then transistors, like outside of computers, they're used as they're made out of a semiconductor, and they're used as a switch. So they can either amplify a current, or they can like stop it, because that's what a switch does, right? And they can also reduce like the strength of the current. So this is what the Hydro gate is trying to show.
Can you talk about why it's so difficult to make machines that can actually manufacture, use photolithography to manufacture sort of advanced semiconductors like 2 nanometer, 3 nanometer? Why is that so difficult? Because to my knowledge, there's only like one company in the world that actually does that.
So yeah, basically, nanomaterials is obviously kind of hard to implement into any industrial application because of obviously how small it is. So maybe that's the reason. So basically, just getting to that more of that. As I mentioned, the electron microscope allows you to go into more of the nitty-gritty areas. Allows you to, get a more of a visual representation of what's going on deep inside, and something that doesn't allow. Because it doesn't. Light would it wouldn't really reflect off something that like electron does.
The wavelength of light that we use for optical microscopes also isn't short enough.
So I think that gets to this question. What do you have to do photolithography at 2 nanometers?
So in order to do photolithography at 2 nanometers, you're going to have to use really small wavelengths. Like one of the smallest is gamma, but obviously that's not really safe for humans. Cause it's really bad for you. Even if you're protected, there's always a chance that it might accidentally come at you or something. So then the safest one for humans is X-ray, which is pretty short, but obviously not short. Humans are okay to contact them, cause people get X-ray scans and stuff. But then X-ray is the way that you would get a smaller you would do photolithography smaller, because the wavelengths are smaller, so it's a lot better. It's a lot easier than normal visible light for to be more precise.
What you said is right, 99%. X-rays actually go right through you, like you said, so they don't do photolithography because they just go through things. To do photolithography, the light has to be absorbed. So you actually use something called soft X-rays or vacuum ultraviolet, which is between X-rays and light. And it doesn't go through anything. It's really annoying, and it's really hard to use. But that's what you need, because it does have to be absorbed. But what you basically said was all right, except it just has to be a little longer wavelength than what you said in order to interact with your photoresist.
Okay, thank you. Okay, and who is our artist? Alex.
Yeah, wait, okay. I didn't really expect this because I haven't even gotten this back yet and finished it pretty late last night, or actually early this morning. But I think, you guys captured everything really well. The one thing that I did kind of try and hint at was the resistance between the big arrows, the bigger arrow with the guy on the smaller canal, and then the smaller one on the bigger canal. I mean, I didn't relate that to the width or anything, and it was kind of vague. So that was really the only thing that I kind of inferred that you guys missed. Like I said, it was very vague and probably hard to interpret, but everything else was spot on. And yeah, I did miss a few things because 8 topics is not easy to get in one picture. But honestly, I'm shocked, and I guess thank you guys for choosing it.
Okay. Group 5. Group 5, please.
Okay, I just want to preface with this is for our supercapacitors experiment that the students performed this morning. Okay, we're doing the other one. Sorry. It's still your group. We just have to switch it. So they prepared this morning. I mean, they did this experiment this morning, and then they drew this during lunchtime, and now they're presenting it. Okay, so sorry. You guys are group 5, but this is the image. Yes, see the red line button? You can also put it in the stand if you want.
Okay. Hi everyone. Thanks for coming today. My name is Claire.
My name is Frank.
And I am Hushin.
Our presentation is on supercapacitors, and we'll be analyzing an analogy that compares and contrasts the supercapacitors with batteries. So first I'll be talking about what do we literally see in this drawing. So up here we have a freezer, and here we have a mini fridge. And then here we have a packet of peas, and as you can see, the arrows show that it goes into both, that one pack goes into the freezer and one goes into the fridge. Here we have a clock that shows the time, and you see the two different paths of following the freezer and the fridge. And in the freezer, it takes more time. It takes like several hours for the whole process to complete, and in the fridge, it takes a lot less time. And then here we have the arrow going one direction, and here we have the arrow going two directions. And then on the final slides, we have on the pathway for the freezer, the peas must be cooked before this bear can eat them. But in the mini fridge, the bear can just eat the peas immediately.
Okay, so the main concept that this picture is trying to show here is between, oh sorry, I got a laser pointer at me. Okay. So the main concept is between the battery, which represent the freezer here, and the supercapacitor, which represent the mini fridge here. And the P here just represent the energy flow, which goes from top to bottom in each pictures. And then, as you can see, the freezer has more capacity, which is why it represents the battery. And then the mini fridge here has less capacity, which represent the supercapacitor. And what a supercapacitor is that it is a electrochemical storage device. It has similar function to a battery, and it discharges and charges electrical currents to fuel up systems. And then, I'm not sure if you can see here, but this thing, this clock, it says 1 o'clock, and this clock here, it says 4 o'clock. So what essentially is that it's trying to say that the freezer, which represents the battery, takes up like more time to be able to serve the P, which represents the energy, to the little cute bear right here, and then and then the mini fridge here, which represents the supercapacitor, it takes like approximately 1 hour to serve the energy flow to the beer, sorry. And then, and also one thing is that here we can see this arrow goes both sides. This means that the supercapacitor goes both ways, so it is a reversible reaction, while on the other hand, the battery discharge is single way, and it cannot, because after the P is cooked, you cannot like reverse it and just put it back in the freezer. But this thing, you can put it back into the fridge. And also, one thing is that I think this is trying to say is that the freezer kind of involves more processes. As you can see, you need to take out the freezer, and then you need to cook it thoroughly, because the freezer freezes the P like to a very cold state, which is why it takes longer time. And yeah.
Yeah, we know it is a cute picture, but it still lack of some details and limitation. There's still some limitations in the picture. Can you hear me? Yeah. Okay. So we know that it lack of showing the lifetime, because we know capacitor and supercapacitor both have longer lifetime than battery, because battery have so many chemical reactions inside, but supercapacitor only have physical phenomena, as it only have the based on the separation of the ions on the surface. Yeah, but it doesn't mean that chemistry is poorer than physics. So what we did today in brief was to compare the lighting time of LED lights. So through this experiment, we found that supercapacitor always provide much more power and can be charged in seconds. But by the way, yeah, we still learned we should check our circuit carefully to avoid the short circuit before power on, because yeah, our lights got smoking many times, yeah, almost burnt. So this is what I think we learned today.
Very nice job explaining this. The analogy makes more sense after you walked me through it. I have a question. So we're talking about supercapacitors as opposed to capacitors. What makes them super?
Okay. So basically, the supercapacitors, I think, have more surface area than regular capacitors. So in our experiment this morning, we used activated carbon as like our material, and that part is the nanoscience aspect of the experiment, because when you for example, if you take a cube and then like just one big cube, you'll have less volume or more volume to surface area, but then if you break it down into more pieces, then there's more surface area per volume. And basically that's a similar concept with activated carbon, or activated charcoal, which is carbon, because it's porous, and so there's a lot of surface area, and it has more room for like the charges to attach. And so that, as opposed to a regular capacitor and to a battery, there's just a lot more power to go around per like unit of area, I guess.
Nice job.
So just following up on that, good answer. So assuming that P's are charges, where are the charges stored in a battery versus a supercapacitor? And how could you possibly, I don't have an answer to this one, imagine modifying this picture to capture that difference in where the charges are stored?
I think battery has as I said, that I'm not sure if it is correct, and it has some chemical reaction inside, and it is based on chemistry. But the supercapacitor and capacitor, it have some ions on the surface when it gets charged. So when you need to charge something, it just separates the ions on the surface. So maybe one is a chemistry and one is a physics.
As a chemist, I say they're all chemistry, but maybe the physicist would. Okay, but what you said is just right. So the battery, it's stored in the interior of the grain of the material, so that could be inside a refrigerator. But how could you possibly modify this to capture the idea that a supercapacitor is stored on the surface?
You mean through this picture?
Yeah.
No, I didn't. I didn't get it through this picture. That is what I learned on class, and what I asked the teachers. I got this. I got this answer.
Yeah, no. I'm saying, how could you imagine a way you could change this picture so that you could capture that component of the behavior of this system?
Oh, sorry for misunderstand you. So can I answer?
I think what we could do here is like sort of like there's some shelves in this like the how do you say this the grocery stores, like they have some sort of but they have similar functions to refrigerators, so maybe we could do like open shelves, but they can still like protect the freshness of the food, and that might be able to work as a like the supercapacitor.
Yeah, anything where you sort of put the peas on the surface of something as opposed to inside them. Yeah, good job.
Great job, guys. Okay, so this is our supercapacitor group that you'll see later on in the presentation who drew this image. So a team of 3 drew this image here today. Okay, so group 6.
Okay, I'm Henry.
I'm Amanda.
I'm Daniel.
And we have an analogy. You can hear me through the microphone, right? Yeah, okay. And here we have an analogy of this very muscular man, and he's punching this bag right here, and we can see the first panel, second panel, he's making observations based on how the bag moves. And yeah, so in this analogy, he's going to be punching the bag, and he's going to be trying to find out, you know, why the bag's moving, and yeah.
Okay, so the first 2 panels show indirect measurement. So in the first panel, the man is curious about his strength. So in the second panel, his solution to that is that he creates a setup where there is a soccer ball right under the punching bag, and the force transfer from his fist to the punching bag would then be transferred to the soccer ball, which then sends the soccer ball flying. And he will then measure the distance which the soccer ball flies to indirectly calculate his strength. And I also think this shows how indirect measurement can benefit scientists because it utilizes graphs and variables, which are common in scientific works, I guess.
Right, so that's indirect measurement. We look at this third panel here. Basically, this is an analogy to constructive interference. I think it was talked about before, but basically constructive interference is when 2 wavelengths with the same peak on the same like y-plane, if they're on the same line, then they will add and create a wavelength that is double of both of the original waves. And that's what the analogy we see here. So here he punched it with 1 fist, it moves, he calculates the distance, and this dialogue right here says it swings higher with 2 fists. So he's punching it with 2 fists, he can see that the bag swings higher. Yeah, that's the analogy.
In panel 4, we see destructive interference where the guy hits the punching bag on either side with both hands, causing the 2 wavelengths to cancel each other out so the bag doesn't move. It stays in place. And then there are some limitations. One is that there are a lot of speech bubbles where I think you don't need that many. It's pretty clear. So, but others is like some concepts weren't covered, which were questions 3, 4, and 5.
Just before we go to the questions, I just have another limitation I'd like to add. It would have been nice if we had like some sort of scale based on how much the bag moved, like an angle from where it was standing, just so we could actually see like, oh, because of the constructive interference, it moved like twice as far. But anyway, so some of the questions that the analogy did not address, or the concepts that the analogy did not discuss. Well, we have question 3, which basically says, how can we measure light? How can we use light to measure distances in the nanoscale and in the scale of the universe, so like galaxies? Well, the observable universe as we know it is 45 billion light years across, which is a number that none of us can really process. And the nanoscale is 10 to the 7th, minus 9. Sorry, minus 9. Even better because a billion is 10 to the 9th. So you can zoom in just as much as you can zoom out. So we can use light to measure distances of hundreds of nanometers using optical microscopes, and we can use light years, which is the distance that light travels in 1 year, to measure very large distances.
Okay, so another question that wasn't really covered in this graphic is how can an atomic force microscope see small objects that an optical microscope would otherwise not be able to? So an atomic force microscope utilizes a needle with a 1 atom tip, which is around a tenth of a nanometer, to feel the surface of a sample, which then sends that information to a computer which models it. And meanwhile, an optical microscope shoots rays of light or photons at a sample, which then bounces back, and the microscope then captures it and also, I guess, creates a model. And the problem with that is that the wavelength of light, visible light at least, is 400 nanometers to 700 nanometers, and there are like objects that are much smaller than that. So objects are much smaller than that. Light wouldn't really be able to create an image with a good resolution, but an atomic force microscope, which is the tip is a tenth of a nanometer, would be able to do much better job at that.
Just with the AFM, with the atomic force microscope, it basically measures the topography instead of like actual light, which has different uses, and when you're like measuring stuff. So the atomic force microscope is sort of limited, but yeah.
And the last question is how nanoscale changes affect like the changes we see. So an example would be an experiment that we did making nanospheres and nanostars. The shape of the spheres reflected a different color, which was black, which is the change that we see. And then when we altered the shape of the nanoparticle to a star, it reflected red, I believe. Yeah. And so changes on a really small scale can have a really big change on what we see and what we perceive. Yeah, that's it.
Thank you.
Questions from the audience, please.
Oh, also to the physicists in this room that are far more, they far understand the concept of light years. I'm sorry that was very butchered, but yeah.
Okay, questions from the audience, please.
Okay, I'm going to go back to a similar question I asked for the other group that presented this about constructive and destructive interference. And the way we talked about it in terms of waves. So, could you suggest a way to modify this diagram that could capture some of the dynamic nature of constructive and destructive interference?
Yeah. So in this diagram, it's sort of limited because we only see basically this punch forces. It's the amount of force put into the bag, which would be the peak. But we don't actually see the bag swinging back. And that's part of the wave. Like you see the peak and then the trough, which is like the lower point. So I guess the diagram could have also shown like the bag swinging back and forth to show like more parts of like the waves of each punch. The amount of force should show like the trajectory of the bag and how it actually moves, if that answers your question.
Yeah, and like I don't go to the gym, but I've like seen things where people like take a punching bag and go.
Are you talking about a speed bag?
Dynamically hit it from opposite sides.
Are you talking
and
about
it
like
just wiggles around, but doesn't really move?
Are you talking about a speed bag where you hit the bag and from?
I don't know what I'm talking about. You need two opposite sides. So the things you just hit repeatedly actually just are a short spring, a short restoring force. That has to be something where you actually have the destructive interference. But yeah, I think that there is an opportunity to get that dynamic wave concept. Waves are weird. Physicists understand waves and nobody else does, pretty much. But when you can think about them, it describes really a lot of the world.
Other questions from our audience, please? You're carrying the team. You're doing all the group project work.
Thanks, Dad.
So it's possible I just didn't understand part of the presentation. I understood when you mentioned using light to measure the universe. Can light be used at the small scale in nanotechnology as well as a unit of measurement? Did I hear that incorrectly?
So you can't really use it to measure things, but you can look through a microscope and you can use that light at that scale, which is 400 to 700 nanometers. Can't use it to actually measure the distance, but you can use it to see things at that scale. As far as measuring, like you would look in a microscope and the computer would be able to tell you like the distance between like different nanoparticles. Like you could zoom in and be like 20 microns or even nanometers with the SEM and TEM. But as far as like measuring distances, light can be used to see things at that scale, not necessarily like measuring it, because you can't actually see like the individual photons, if that makes sense, or, like the rays.
Did anyone want to add anything onto that?
You kind of can't use it to measure super small things because it ends at around, I think, 250 nanometers.
Of resolution? Yes.
Yeah.
So what do you use instead?
You can use electron microscopes or the AFM or, SEM too, the scanning electron microscope.
But can you actually measure in some ways? Can you use the fact that you know something about light as a way to actually measure things?
Yes, you can. So I guess you could use an optical microscope to try and see if something is smaller, but you can't actually tell like what that is. So if it was smaller than 300, 400 nanometers, wherever light is small, but you can't actually see anything because the wavelength would just bounce off. It doesn't catch on those small things. So you could be able to tell that it's smaller than light, but you wouldn't be able to tell how big that actually was.
I have something to add on. So if I'm understanding the question correctly, so he said like light years, right? So light years kind of like the distance light travels in a year. So if you want to have like a really small distance, you could say maybe like, I don't know, light millisecond or something like that. And
I think what we're trying to get at is, what did you do in this experiment, this measurement at the nanoscale experiment, right? So we had red laser light being shined through something, and you measured something at the nanoscale. So could you perhaps describe what that experiment was?
so we used like a diffraction grating. We shone a laser to a diffraction grating, and the light kind of like split up because of constructive destructive interferences.
Right, and how did you then calculate the size of your diffraction grating through an indirect measurement?
We kind of used the a squared, b squared, c squared. Is that Pythagorean?
We use trigonometry to calculate diffraction angle based on the variables we had already measured. So we used, we calculated, I think it was the sine of like the distance that we'd measured, and then we used the angle to calculate the diffraction angle, and then we found the actual distance, which was d. We had a formula for that though. So.
But it wasn't just the angle. You actually needed something to calibrate that angle and turn it into a physical measurement. So you used something about the light.
Was it like
the we used the wavelength?
You used the wavelength, which means you were using light directly to measure something at the small scale. You were basically comparing the wavelength of light to the structure of your material, and from that you were able to back out what its structure was in an indirect way.
Okay, great. Thank you, guys. Okay, now we are going to take a 10-minute, 5-minute intermission. Let's be back at 3:47. Acknowledge Hong Shen, who is our artist. Thank you for this great drawing. Is there anything you'd like to add?
Yeah. So what I did on the first day was to draw something like even the children can understand what is indirect measurement and what is constructive and what is deconstructive. So I want to make everyone understand these 2 points, these 2 key points. So I didn't mention someone else. Yeah, something else. So yeah, this is my limitation. Thank you for telling me this. And what I think is like maybe you have some misunderstand in this wavelength, and if you have still have some questions, I asked the teacher so many questions on the first day, so I have understand it clearly. So if you still have any question, you can ask me. I can help you solve it.
Great, thank you. Okay, group 7, come on up, please. Okay, I have this one. We have this one. Who wants our laser pointer?
You could give it to Jason because Jason's starting.
Okay.
All right. Hello, I'm Jason.
I'm Alex.
Amy.
All right. By a show of hands, who knows why you see colors? Why am I not seeing all the students that came to this camp raising their hands? All right. We know somebody didn't pay attention. So, we're here to talk about the science of plasmonics. And to help you, we have a comic. So what we see here is behind the scenes of Toys R Us. We have several toys going on a conveyor belt, zooming toward our dyeing section. And here we see one of the toys being dyed a different color. But here, in the third panel, we see our manager who is observing the process and has happened to see that the dye ink has missed the toy. This is in relevance to plasmonic resonance, where the toys which are shown at moving at a speed is similar to how a frequency of light relates to the color it comes out. So the toys come out at a similar speed, and that speed relates to the color, and if the frequency is wrong, then the color won't be the same.
Can I have the laser thingy? Yeah. Thanks. Oh, never mind. Sorry. Okay, so the second row you see there's like a big man and then a little petite man, and there's like the red ink over there. So in the middle section there's like the big man, and he's like getting dyed only a little bit. He's like half dyed, and then the red one is like, well, the tiny one is like completely soaked in the red dye, and the last one you see like the big man is pink while the little man is red, and the manager is being like, their colors are different. And that kind of relates to like the plasmon resonance kind of thing, because size and shape are what the process, like the color you see depends on. So for smaller nanoparticles, because they have like a denser, what's it called? Well, the big one, because it's bigger, it's gonna take a different like color compared to the small one. And yeah, the amount of like free electrons that are in the red ones are like denser than the bigger one.
All right, so on our last drawing, I mean, we have a spherical object, and then we have a person. So this is supposed to represent the difference between transmission and scattering, like the other plasmonics group said before. I'm going to use a different analogy, maybe like to add on. Transmission is where the light goes right through the object. So imagine like a pane of glass and just light shining right through it. And scattering is like a mirror where the light is reflected and reflected off of that object. and it does not pass through. So, I mean, we have our little guy, we have our spherical object, and they're both getting inked. So, the ink, as you can see on the spherical object, is getting, it's getting scattered, it's getting sprayed all over the place. It's going to be a big mess. And you see the ink, for whatever reason, I don't know why, I don't think humans are supposed to do this, but the ink is being absorbed by the little person that we have. So the little person absorbing all of the ink represents the transmission of light going through an object, and like the splattering of all of the ink on the spherical object is representative of the scattering of light, and there's another guy that says it gets messy, referring to like all of the scattered light all over the place, not the transparency, or not the transmission of light. So while this is a great cartoon, it does have some limitations, one of which being not including an analogy for the photothermal effect. So to put it in layman's terms, the photothermal effect is when light is converted to heat. I'm not from here, and Los Angeles is really sunny, so whenever I walk out in dark clothing, all of that, like sunlight, gets absorbed into my dark clothing, and I get really hot. And it's uncomfortable, I'll be honest. But that is, simply put, a simple way of explaining the photothermal effect. Now, this is used with metals and other things on the nanoscale, but, to put it very simply, it is when light is absorbed and turned into heat. I don't know how they could have depicted this. Maybe they could have had, like, a heat lamp or something, and, like, the person absorbing or taking, like, or maybe not a heat lamp, but, like, maybe they could shine a light on the person, and then the person could like get visibly warmer with some sort of temperature, but I'm not really sure. Yeah.
That's it.
Okay, so I think this is a concept that a lot of people might have struggled with a little bit, so I want to help clarify this with you guys by asking questions. So you were describing the photothermal effect in your sort of analogy as you being in LA and there's the sun and you're wearing clothes and it gets hot. Can you describe the photothermal effect as you actually observed it or as you saw it in the lecture or in the lab?
So in one of the lecture examples, they said that you could use the photothermal effect by coating cancer cells in like these shells of gold and blast them with infrared light. So like the group before us said on plasmonics, when you're on the nanoscale, it's way smaller than when like where you can see most visible light. So metals don't have the same properties as we observe them. They're not shiny. They're a very like dull, lackluster object. So they're going to absorb that light a lot better than they would, on the macro scale, because metal, as you could see, kind of reflects light here. So on the nanoscale, when we're blasting these cancer cells with, infrared light, because it's not reflective, it absorbs this light, and, that light could be transferred into heat because metals are good, like notoriously good conductors of heat and kill the cancer cells. We didn't actually use, correct me if I'm wrong. I don't think we actually experimented with the photothermal effect in our experiment with gold nanoparticles, but I think the cancer cell representation was the best analogy that I could kind of use that we learned about.
Yeah, so then in that analogy, is it just the fact that it's infrared light? Like, what if you used a different wavelength of light? Would the same thing happen, and why or why not?
I believe the same thing would happen with different light. I'm not completely sure, but, light can still be absorbed into heat with metals because light carries energy. and metals are good conductors of heat. So whenever there is an introduction of energy into metals, like they can hold that heat. I'm not completely sure, but I think that is like the way I can answer that question to the best of my ability.
Well, maybe just to give you sort of a little clarifying hint. So the lab was about what again?
The plasmonics of gold nanoparticles.
Right? And what is that? What was happening with the light and the particles?
Oh yeah, the light was being scattered depending on the size of the particles.
But what was happening with the nanoparticles as opposed to a bulk material? Surface plasmon
resonance.
Yeah. So then can you describe how the surface plasmon resonance is actually causing the photothermal effect?
I was gonna say something, but then you completely said a different thing, so I actually don't know anymore. I was just gonna talk about how the colors, they're different, like how one of them turned into be like a dark purple, and then we shine the light a different way, it turned up into like ruby, and how we at the end we combined the nanostars and nanospheres together. So if you shine the light one way from the way you were looking, it was like a dark dull brown, but then you shine it from the back, you got like a nice shiny color, red color. Sorry, not shiny. Okay.
Yeah.
So then, so the resonance is doing what?
So the resonance, so I guess it's resonant frequency, where the resonance of the wave of light is the same as the resonance of the electron. So what the plasmon resonance does is when you have a resonant frequency between a ray of light and an electron, I mean, correct me if I'm wrong, but with visible light, it produces a contrasting wave of light. So if you shine, like, I don't know, if you shine red light onto like a gold nanoparticle, or if you shine red light onto something, or onto an electron that is, you know, within the no, not the photothermal, plasmonic resonance, then you should get green light coming out of it, or green light should be visible to us. Right.
If you can't get green light on if you put red light in. You got to
Right.
green light out. You got to start with white.
Okay.
And then there's a different path for the green or the red.
All right. So for those of you who don't understand, like how I asked everyone why you see colors here, right? So if I have an apple, and if I shine, let's say, light from the sun hits the apple absorbs green light. So there's a color wheel, right? And so it gives you different colors. So we got red and green on the opposite side. And if the apple's red, well, mostly red, if the apple's red, it absorbs the green light and reflects the red light. So that's why you see the apple is red.
And so that's right. So that plasmon resonance is the light that's absorbed. The frequency of that plasmon resonance is the frequency of the light that's absorbed. So in order to get the photothermal effect, what kind of light do you have to shine on your material?
Like a light that is the same frequency as like the metal that you want to be heated up.
Exactly. And the metals are just crazy good at turning light into heat. They're uniquely good, better than your black shirt, at turning light into heat. And that's the cool thing about this effect. Good job.
Thank you.
Thank you.
Thank you so much.
So who is our artist for this one? Anything you'd like to add?
Thank you for great explanation about my cartoon.
Thank you.
Okay, group 8, please.
Hello everyone, my name's Derek.
My name is Elizabeth.
And my name is Anna Peck.
Yeah, so today we'll be talking about emulsions. So as a background, emulsions are fine droplets of different substances that are mixed together to create like a really mixed substance. And thermodynamically, emulsions are they want to separate themselves, so they are very unstable, and they would want to separate really quickly. So some ways we learned in the class to stabilize emulsions is through stabilizing agents and also mechanical stabilizers. And an example of a stabilizing mechanical usage is using a frother to mix oil and water together to create a really fine mixture. And but we also learned how to use microfluid devices to mix these emulsions through fine droplets by like slowly adding them together and create a really fine substance, so then that it would be harder for them to separate.
So next, I'll explain about the photo that we did. So in the image, there are two cats fighting, but by dreads and feet, they become peaceful. This is related to emulsion. Two cats are water and oil, which are nonpolar and polar molecules. To explain briefly about nonpolar and polar molecules, the polar molecules has different charge ends, like negative charge and positive charge, but nonpolar doesn't. And also nonpolar and nonpolar mix together, but and also polar and polar molecules mix together. So this is immiscible fluid, which do not mix and separates into two posits. And as you see, after we give feed and dreads to cats, they become peaceful. This is stability of of emulsion, which can achieve by emulsifier. So dread and feed is emulsifier, which made them peaceful. When we put emulsifier like soy lecithin in water and oil, then they mix well, but later they separate it again, which can be described in this photo. And on the bottom of this cartoon, there is like cats like fish, one cat's like fish, and one cat like meat, and one dog like both of them. This this represent hydrophobic and hydrophilic for these two cats because it has different properties, which has water fearing and water loving. And for the dog, it's like amphiphilic, which is like have both water fearing, both water loving.
So moving on to the limitation of this analogy. So there are two missing concepts of this analogy. So the first one is microfluidic devices. This is a system that manipulates small amount of fluids by using a small channels. It will brings together two slip strings into a single larger channels. So in the experiment, we use water and oil. And another missing concept is self-assembly. This is a process in which molecules will form by themselves, and it creates self-assembling that thermodynamic better for them. And we think overall this analogy cover a lot of scientific concept really well, and that's it. Thank you.
Audience questions, please.
Hi. Okay, so I really like the art, and I kind of want to know like
what you guys think, or which concept you guys think was best depicted in this comic?
Um, I think, I think for this cartoon, it is really easy to understand because when we give feed and dress to cat, it become peaceful. As we did in experiment, we put kind of soy lecithin and gelatin and sugar in the water and oil, and but it mixed first. It mixed well first, but later it's separated. So I think it depicts well in this cartoon.
I guess sort of elaborating on the idea of the emulsifying agents and the mixing and all of that. So you said, you know, if you give food or treats, they both will mix. Wow, this chair is totally falling apart. That if you add food or treats, that they'll mix together. But I'm curious if you would think that they're mixing equally between those two options, and you know, if not, what's the difference? Like, how would you describe, you know, one maybe they're mixing a little bit more, and then one they're mixing a little bit less? Like, how would that be maybe an analogy to what you did in the lab?
So I feel like in the lab, soy lecithin lasted the longest, and I feel like that's like comparable to them playing, because they, after like eating, like they will have like the most energy to like stay together, and that's also kind of what happened in the lab, where it took the longest for the soy to separate.
Okay, thank you guys. And who is our artist for this one?
I really like the like how you guys analyzed my art, and just one thing I wanted to add. If you guys mentioned it, I'm sorry I didn't catch it, but like on the fourth part, it showed that like an hour later that the cats were starting to get mad again, because I wanted to depict the fact that like both like emulsifiers or like mechanical energy cannot fully mix the two things, and it'll like separate again at one point. But yeah, the rest is really good.
Thank you. Okay, group 9, please come up.
Hi, hi, I'm Rachel.
I'm Will.
I'm Reynard.
And okay, so have you ever done your nails? If not, no worries, because this is the process to get your nails done. So, this lady, she needs help with her nails. So to help her, we're gonna start with applying glue to the surface of her nails, and then we're gonna apply acrylic nails to the area where you applied the glue to her nails, and then you're going to dry the glue so that the nails stick. So you're going to put it under the UV light exposure, and then you're not gonna dry your nails under the sunlight because it would take too much time. So you're gonna use the UV light, and you're gonna use a small brush to coat the nail polish on the nail, and you're not gonna use a big brush because it would make the nail polish like leak off the nail. And then you're going to use filing to even it out. And when you file your nails, there's like nail shavings, so you're gonna like wipe it off with a cotton swab, and then you're done.
Yeah, so these steps of getting your nails done are emulating the steps of photolithography, and this can be seen in all these steps. So first with the glue, this is mimicking the photoresist, which you coat onto the a substance, and then in the second step where you put on the acrylics, this is emulating the mask that you put on the layer of photoresist to cover parts of it, and then you expose to UV light, and this is showing that it's going to take longer in the sun because the wavelengths of light from the sun are a lot larger than those of the concentrated UV light, and then that's exposure. And then in the fourth step, or where you paint on the pattern, that is corresponding to the develop stage in photolithography, where you take away the first layer of photoresist that was exposed to the UV light. And then in the fifth step, that corresponds to etching, where you take away the copper that was underneath the photoresist. And in the sixth step, you take away the last layer of photoresist that wasn't taken away before in the fourth step. And so some limitations of this analogy are in the fourth, fifth, and sixth steps, because in the fourth step, in the developing stage, for photolithography, it's going to take away the first layer of photoresist that was exposed to the UV light, whereas in this analogy, you're actually adding on something. And this step actually also touches on the concepts of using smaller instruments for finer details and features, because you can see the bigger brush, it can't really get any pattern onto the nail, whereas the smaller brush, or the smaller and thinner brush, can get finer details onto the nail. And limitation in the fifth step is in photolithography, this step of etching is going to take away the copper layer underneath the photoresist, whereas this just is taking away the tip of the fingernail instead. And in the sixth step, that only wipes off the excess shavings, whereas in photolithography, it would take away the last remnants of the photoresist.
And yeah, so the other thing with photolithography is there's a lot of concepts to it, so you couldn't really use all the concepts. And so some of the concepts they couldn't present in their picture. One was parallel and sequential processes, which is in industrial processes. You can do like the regular sequential. This is more like sequential, where you do one at a time. Or you could do parallel, where you do, so lithography is like wafers, and so you could put many patterns on the same wafer, which is the same as parallel sequences, parallel processes. And then there's also, that ties to that, there's Moore's law, which is about transistors, where that every 2 years, the amount that can be produced will be doubled, and the size will be halved. Sorry. And then the next one is resistivity and resistance. They weren't able, but that is tying to resistivity, ties to the material that is used. Like in wiring, you'll have like a copper wire with a bigger diameter or smaller diameter will have the same resistivity, but resistance ties resistivity plus the area, the surface area, and the length of it, or the diameter, which resistance is it's the combination of resistivity plus the length over surface area. Then the sixth one is the transistor. And that is like, transistors are switches. Like if you have a pipe, like a water pipe, and you have like a manual lever to it, a transistor is like the electrical version of that. You'll have like, you'll send a current through it, and that'll be like opening the pipe, which allows the rest of the current to go through. But when you turn on, when you stop shooting the current through it, then it's like closing the pump itself. But you can do that in a computer multiple times without having to have like a manual switch in there, which can let you do many other processes through it. The seventh one is a clean room, which these nanochips are very tiny, so any little disturbances to these, which might be not bad to most things, but when you're at the very tiny level, these nanochips can be really heavily disturbed. If like one particle of dust lands on them, it could pretty much ruin the entire chip. So these clean rooms kind of keep that all safe from all the dust particles. And the last one is the SEM machines, which is the scanning electron microscope, which instead of like a light microscope, just shines light onto it so that you can see it through the eye, like the lenses. Scanning electron microscope uses an electron gun to shoot electrons onto the surface of it and bounce it off so that you can, or it scatters it across it so that you can pick up the scattering electrons off of it. Which is how you use electrons instead of, and you use the electron microscopes instead of light microscopes because electron microscopes can see a lot smaller because the optical resolution of visible light is only 200 nanometers at its smallest point, while electron microscopes can go really as small as you want them to go, but they'll destroy their substance if you go really below if you go below nanometers. So yeah, that's it.
Audience questions, please.
So you mentioned that you thought this might be more sequential processing. I sort of interpreted this as parallel processing. So if you were thinking of this version as parallel processing, how would sequential processing then have been the analogy here instead? Like, how would you have changed this?
Okay, yeah, no, I was thinking like it as one as a whole, but technically you have all the fingers as different processes. So sequential would be just doing like one nail instead of doing all 5 at the same time.
Any other questions? Okay, and our artist. This is Amy. Anything you'd like to add?
Thanks. Like, you got something I didn't even think about. So that was kind of cool. Thanks for the points, I guess. And I don't know if you could tell by this, but I'd never done my nails before. I'm sorry. So like, I kind of messed up on that, but I think you guys got some really good points, and you explained it like better than I could have, and like, you did great. Thanks.
Thank you. All right, thank you. Okay, group 10, please.
Hi, I'm Princess.
Hi, I'm Frankie.
Hi, I'm Trinity. Okay, so I'm going to be starting us off by explaining what we literally see. So, thank you. Does this work? Hold up.
The middle.
Oh, okay. So in the first panel, we kind of see a map, and there are 3 different types of land masses. Like, one's an island, the one in the middle is like a group of islands, and then the one on the far right is just like a really big island, or like a bigger country, I think. And then in the second panel, we can see a comparison of 3 different things again. So first, they're different tradeways. So the first one is like one boat carrying some like or some goods, I think. And then the second one is like a group of boats with goods again. And then the last one is just like a herd of camels also carrying goods. And then in this third panel is different or varying types of goods. So the first one's like a small amount, then there's a medium amount, and then there's like a really large amount. And then in the last panel, oh, okay. And then in the last panel, you can see that this boat here is like nice after some time. These are also okay, but these camels are dead.
Okay, so I'm going to start with the analogies. So in the top left, we have our set of islands. Each are labeled C for capacitor, S for supercapacitor, and B for batteries. The map depicts how much quantity of energy each item can store. Capacity storing the least amount of energy, supercapacity storing the middle amount, and then battery storing the most. To the right of that, we have our methods of tradeways, or the amount of energy flow coming out and the methods in which they come out. So our boat analogy to describe the fact that the supercapacitors and capacitors have energy flow out of them way faster than the batteries do. So the top left would be the boat representing the capacitor, because there's a little amount of energy coming out of it, but at a very fast rate. The supercapacitor is sort of a middle ground between the two, and then the batteries are described as camels because the tradeway is across the really big island, but at a really slow rate.
So now moving on to the bottom left panel, which depicts the amount of goods, which is also equivalent to the capacitance of the capacitor, the supercapacitor, and the battery. So the one with the smallest quantity of goods, that would represent the capacity of a capacitor, as it can only store a really little amount of charge. And the middle quantity would depict the capacitance of a supercapacitor, because that's the middle ground between a capacitor and a battery, while the battery can store the most amount of energy, which is shown by the largest amount of goods. So the years later basically talks about the how batteries degrade the most, while capacitors don't, or not as much. So the boat with like the shiny effects, that represents the capacitor. After many years, it's still in really good quality. Then the one with few boats, as you can see, there aren't the shiny effects, so they're okay quality, which shows the supercapacitor, while the dead camels basically show that the batteries are dead. Yeah.
So then I'm going to be discussing the limitations. So I think that this was a really good cartoon considering the short amount of time that they had to draw. But I think one key concept that they didn't include was that the main difference between capacitors and batteries are that, like, in order to release energy, batteries require a chemical reaction that is usually irreversible, I think, whereas regular capacitors just directly release energy. And then another thing is probably the labels. You can't really see them on here, but you can see there's like C, S, B, which is supposed to represent capacitor, supercapacitor, and battery. And yeah.
Ooh, we've got some parent questions.
Thank you. Yeah, I'm just wondering, does battery, does it have disadvantages? Can you discuss the advantages as well as the disadvantages? And on the concept that you have, the analogy that you have actually shown, what was best represented in nanoscience? What is the relevance?
So batteries have many disadvantages and advantages, with them having the most capacity to store energy in them. They're often used widely the most. However, as mentioned before, they have irreversible reactions within them that mean they are really a finite resource, meaning we can't use them as often, or as they're not as renewable as alternative methods such as the capacitors and supercapacitors.
So how does this relate to the, nanoscience part? So I think the main part that relates to it would be the supercapacitors, as the supercapacitors have nano-sized particles, and this increases the surface area within them, which allows them to store more charge compared to the capacitors, which make it a middle ground between capacitors and batteries. Yeah.
So I think there's one additional difference between a battery and a supercapacitor that's depicted here. And I think it's specifically the choice of animal that they chose for B. Can you guys maybe think of like the extra difference between a battery and a capacitor that might be shown here?
Yeah, so I think the difference is like the speed of charge and discharge. So the camels are usually seen as like slow animals. So the battery is like the battery discharges pretty slowly compared to the supercapacitor, which is discharged like really quickly. So I think that's where the speeds are represented by the different vehicles, like the camel's slow, whereas the boat is pretty fast.
And also, just to add on to that, this is just due to the fact that batteries have to go through a chemical reaction before they can release energy, which is why camels are slower and they represent batteries.
Great. Thank you guys so much. Okay, and then our supercapacitor group that presented earlier are the artists of this, and then this group who presented here were the artists of group 5 presentations. Okay, so group 11, our last group of the day. Please come up.
We're the last group of the day, and I'm like really tired. So, yeah. My name is Darren.
Oh, my name is Harry.
My name is Jason.
And we'll be showing like a pictorial analogy for an emulsion. So first, I'll give some like context for the experiment that we did. So essentially, we used substances that were immiscible or they don't mix, and we like added some stabilizing agents or like emulsifiers into these like mixtures, and then we've made like these like fine droplets. And then when we did this, we like used different types of stabilizing agents to compare how like strong like each one was, and then we also used different forms of like mixing in order to like compare those as well. So I'm gonna like describe this analogy literally right now. So here you have like a bunch of scientists, and then there's a big pot of stuff going on, and then if you move here, there's like these people holding like these like triangular like circle rod things, and then in his other hand there's like a circle with like these squares, and he's saying it's like they hate each other. And then but then after that he gets like a magnet like right here, and then he attaches he's able to attach both those like two different things to the magnet, and now he's saying like now they fit. And then after that he takes like two of the same object, and then he says they fit pretty well. I think that's what it says. And then essentially in this mixture you see that like there's like these magnets, and then they're here with like these like rectangles, and then they're like flowing around, and then they're able to like stick together, and then somebody's using like a big rod to mix these. And then downstairs you have like some device here where there's only like magnets coming through in one channel, and then there's gonna be like these triangular things coming through the other channel, and then one by one there's one magnet and then one triangular thing, and they're moving through this very small channel into like this box. And in this box they're like forming this like this forming this like really cool like structure here, and you can see like a thermometer for temperature.
Okay, well, I'm gonna talk about the scientific concepts in here. So first of all, it's the emulsion, so which is a dispersion of like minute droplets of a liquid in another, which it is immiscible. So the basic wait, sorry. Well, let's talk about oil. Let's take oil and water. Well, in this case, if you put oil and water in a glass, they will not mix. They will form a distinct two layers. However, if you stir it, like using the giant spatula in the graph and you input some mechanical energy, they will mix eventually. However, after a while, they are gonna separate, like the spring or yeah. So this is what a emotion is. And then I'm gonna talk about the hydrophilic, hydrophobic, and amphiphilic. Well, hydro means water, right? And therefore, hydrophilic means to basically attract water, and hydrophobic means to repel water. And amphiphilic is that a substance, it has two parts, and one part will attract water, and the other part will repel water. And then I'm gonna talk about the microfluidic device. Well, it's basically a device that you can see on the graph. Well, it's a device precisely controlling and manipulating the micro scale size fluid. And therefore, you can see that the size of the tube is very small. So it will it will lead to a phenomenon called laminar flow. So it will attribute to a science constant called Reynolds number. And in this case, RE equals to rho VL over mu. And rho is the density, V is the relative velocity, and L is the feature size. And mu is the fluid viscosity. Therefore, in this case, the RE is very low. In this case, the laminar flow will occur. So you can use this to control a less volume of sample, and you can analyze the fluid. And then you can see on the left jar, it's something called self-assembly will happen. It's like a spontaneous formation of disordered particles into a more organized particles. Because in this case, they will like to self-assemble, to gather together automatically. And this will attribute to three things. There are three factors affecting it. And the first one is the intermolecular force, which is basically the stronger the intermolecular force, the stronger the rate of self-assembly. And then it's the temperature. So like if you have a high temperature, as you can see on the graph, there's a thermometer. So the higher the temperature, the higher the average kinetic energy, and therefore the particles can move together with a higher momentum, and in this case they can collide more often with a stronger force. And then it's a concentration, which means that the higher the concentration, there are more particles per unit volume, and in this case, there will be more successful collisions. Okay, that's all.
Wait a minute. Now I'm kind of like starting talking about the limitation of this drawing, and can you give me the pointer? Thank you. So first of all, it's a really well done art piece that's covered all the 4 questions, and then I think really well done for the drawings, and but still some limitations. So I think it's something is ambiguity is this kind of triangle and with this gear. So it's supposed to be some hydrophilic or hydrophobic, but it's kind of like it's kind of like triangle rectangle here, and kind of like different rectangular gear, I think, over here. So it's maybe not that ambiguity. Yeah, so I probably will change it to this gears. And another thing is looking here. So from the talking here, we can know that the magnet is amphiphilic molecules, that it should be kind of like mixed with whatever it's hydrophobic or hydrophilic molecules, so it should mix. But and in the microfluidic device, it usually kind of like cannot mix. It's kind of like have a separate things. So I would kind of like change the magnet to the whatever
the other cog.
Yeah, that things. And kind of like in this one, so they have as Johnson says, Jason, never. Jason says they have two kind of like main part of how self-assembling goes. So one is intermolecular force. So I think probably you can show some intermolecular force, how strong kind of affect the rate of going, something like that. Yeah. Any questions?
Questions from the audience, please.
Okay, thank you. So one of the concepts that we also talked about during the workshop was that the input of energy, right, the mechanical energy that you put into the system will affect how good is the emulsion that you got, right? So do you think any of the things you see on the drawing depict that, or if they don't, what do you think would be an interesting analogy for that?
I think the mixing here just depicts that, but then it doesn't really show that, like, if you have like something stronger, like for example in our experiment we use like frothers, right? So if you have like a stronger mix, then you could create like a more stable emulsion. And they also missed out on like I think they only had magnets as amphiphilic emulsifiers, right? So then if they had like another type of emulsifier that was also stronger, they could have like chosen, like they could have made like a different bowl with that mixture, and that would have had like a stronger emulsification too.
Thank you.
I have a question about the microfluidic devices. So we talked about mechanical energy input with the frother versus stirring versus shaking. But in the microfluidic devices, how do you control the mechanical energy input?
I think you can control the mechanical energy input in a microfluidic device, but like those two like channels over there, you can like control the pressure at which liquid flows through them. So in our experiment, we had like these test tubes, and we would like squeeze them with different pressures, and then that could like regulate the flow and how long your droplets were, and then that could like regulate the microfluidic device.
Exactly, perfect. So the flow rate through the microfluidic device is the analogy for the mechanical energy input. Great. Thank you, guys. Okay, and then our artist.
Yeah, I didn't expect this, but I guess thank you. Yeah, I'm I'm speechless. They described it perfectly, and I think they gave me more credit than where credit was due, because I don't think I depicted all of that. But yeah, I really don't have much to say. I guess thank you, but you know.
Okay, so that concludes our presentations. So students, we'd like you to take this post-course survey. We are always trying to improve our course, so we'd love for you to take our survey. Professor Sarah Tolbert, would you like to say any closing remarks?
Okay, so I want to just say a few things. So first off, thank you guys for all of the excellent presentations. I'm sorry if we asked hard questions, but you guys did a great job of answering them. And I want you to realize that you can answer really hard questions in front of a room full of people. And so I'd like us to give a round of applause to all of our presenters. And parents, if you have any more questions about all these cool concepts, you can ask any of the students, me, any of the graduate student mentors around. There's a lot of cool science concepts here that lots of people are happy to talk more about. But then to end, I would just like to Shailene has thanked all sorts of people. She's thanked our graduate student mentors, all the people at CNSI. But now I think we all need to thank Shailene. Whoa. Every ship needs a dynamic captain on board, and you have been one. So thank you for doing an awesome job. And I think that now we have a reception out in the big lobby. Lobby is the word I'm looking for. Out in the lobby, so a chance to just chat and relax and sort of reflect on the excellent week that we've just had. So thank you all.
Thank you. Students, we'd also like to take a class photo out in front of the CNSI so we can commemorate our time together. So please do that, and parents, go enjoy the reception first.
Yeah. Okay, so go. We're going to do the photo like right now, because once you scatter, you'll never come back. So everybody go outside right